In this lecture, we'll examine the concept of relative velocity. And relative velocity is a, sort of a complex motion where two frames of reference move relative to one another. We already examined situations where we saw frames of reference that moved relative to each other. A great example is the bus. When you're sitting inside the bus and you make reference to somebody else who's in the bus, generally you would refer to their location or their velocity according to the frame of reference of the bus. But obviously if the bus is moving then it becomes kind of complicated. There's sort of a combinations of movements. There's the movement within the bus in that frame of reference, and then there's the motion of the bus, which is moving relative to the ground. And what we would like to do is to look at how we combine those together in an appropriate way so that we can measure the velocity of a person relative to the bus or relative to the ground or to any other frame of reference that might be occurring. And really one of the easiest ways to do this is to just simply look at examples. So let's start by looking at the first example where Jared is walking towards the back of the bus at 1.5 meters per second while the bus in the meantime is moving forward at 6 meters per second. Now anytime somebody is moving backwards, we would refer to that velocity as negative. And in this situation it would probably be very helpful to just draw a simple sketch, nothing fancy. That's my bus. And there is Jared. He is walking backwards. So I'll use a small arrow to indicate his negative 1.5 meter per second velocity. And the bus, on the other hand, is moving forward with a much larger velocity of positive 6.0 meters per second. Okay, so let me just kind of walk you through the process of how you think about what frame of reference are you measuring this thing relative to. So when you ask what is Jared's velocity relative to the bus, with the bus frame of reference, this 6 meters per second is essentially irrelevant. We don't need to consider that 6 meters per second because we're only looking in the frame of reference of the bus. And in that case, for A, we would say the velocity, and this is the kind of the notation that would be really ideal to use. We would say J to B. So this is the velocity of Jared relative to the bus. And in this case, that velocity would be negative 1.5 meters per second. Okay, and that's pretty standard. I mean, you can see that Jared's walking backwards in the bus. But here's the thing that's a little more complicated. What about the velocity of the bus relative to Jared? Again, both the bus and Jared have this 6 meter per second velocity, so that velocity is really not relevant and we don't need to consider it. In this case, we want to know how fast is the bus moving relative to him rather than him to the bus. It's a kind of a weird thing. It's almost as though you want to imagine that if Jared were stationary, how fast would the bus have to move in order for him to have this apparent negative 1.5 meter per second velocity in the negative direction? Well, if he were stationary, the only way he would be able to move towards the back of the bus would be if the bus, relative to Jared, were moving forward at positive 1.5 meters per second. And that's a little bit of a strange thing to think about, but essentially, in any situation, two observers looking at each other, will always give the opposite velocity. So, for example, if according to the bus's frame of reference, Jared's moving backwards at minus 1.5, then according to Jared's frame of reference, if I use Jared as the frame of reference, then the bus would be moving in the opposite direction with the same magnitude, both at 1.5 meters per second. So for B, the velocity of the bus to Jared, that would be positive 1.5 meters per second. That's really a rule worth remembering. Any two observers trying to determine the velocity of the other will always give the same magnitude but the opposite sign. In every situation, whether they go with each other, against each other, the two objects are inside, the person's inside the object, does not make any difference. Two observers with their frames of reference will always give the opposite velocity. Now the point of this whole thing though is to start looking at a little more complicated situations. So Jared moves relative to the bus moves relative to the ground. So in part C, we're trying to determine what is Jared's velocity relative to the ground. So the bus is moving forward at 6, but Jared is moving in the opposite direction within the bus, and so ultimately what we would want to do, this is the velocity of Jared to the ground. In this situation, we want to take into consideration the bus's velocity of 6 meters per second, but Jared is moving in the in the opposite direction, so we would add his negative 1.5 meters per second to end up with a final velocity relative to the ground for Jared of positive 4.5 meters per second. He's still moving forward, but at a slower rate than the overall velocity of the bus. And I think that probably, should make sense to you. You can imagine if Jared were walking towards the front of the bus, then his combined velocity would be greater. And I'm sure you've experienced this if you've ever ridden on a bus. You're walking backwards while the bus is moving slowly, and you might look outside and notice that things don't seem to be moving very fast because you're sort of matching the velocity of the bus, or the opposite. You're walking forward in the bus, and so you're passing things more rapidly than the bus itself is. Also, if you go to the airport, you may notice that there are moving walkways, and with these moving walkways, you can be walking on them, so you have a combined speed of the speed you would walk with plus the speed of the moving walkway. So relative to the ground, you can move much more rapidly. That's sort of the point of those moving walkways. It's not just to allow you to be lazy or to not have to do much work, but it's a way of you getting there quicker, and that's generally how you'll find most people use those moving walkways. So let's go to a kind of a related but slightly different question. And in this one, we'll have Jessica sitting in a car that's moving at 20 meters per second, so she obviously has that same velocity. In the car's frame of reference, she's not moving at all, but in the frame of reference of the ground, she has the same speed that the car has. And we're going to have her throw a set of keys through an open window at 13.5 meters per second. And the question then is, how fast are the keys moving relative to the ground? There is like a formal equation for this, but I think for the purposes of this course, we really want to just kind of keep things simple and just kind of reason out, do I need to add the two velocities, or should I subtract the two velocities to come up with their velocity relative to the frame of reference that you're choosing? In this case, the frame of reference it states relative to the ground. So in this case, the velocity of the keys to the ground is going to be the velocity of the car. In other words, the keys would have that velocity even if she didn't throw them. The keys would be moving already at 20 meters per second. So that when she throws them at 13.5 meters per second relative to the car, and the car is moving at 20 meters per second relative to the ground, we'll combine those two velocities to find a total velocity of 35 meters per second. And so in these simple situations, it's just really simply adding or combining because something is inside of a moving object. This could be a plane, a train, a boat. Cars probably not as well, but maybe like a van, something where there could be relative motion within the moving object, and then we simply want to add or subtract to come up with the velocity relative to the ground. Now there are more slightly a little more complicated problems. Let's take a look at a variation of this problem. And in this example, we're going to have two cars traveling. Now the two cars could be traveling towards each other, away from each other. They could both be going in the same direction, but one faster. In this case, we're going to place car A 125 kilometers to the north of car B. So car A is 125 kilometers north of car B. Car A has a velocity of 65 kilometers per hour, and car B has a velocity slightly smaller of only 45 kilometers per hour. Now the traditional frame of reference in this particular example, anything traveling to the north would typically be considered the positive direction, and anything traveling to the south would be the negative direction. So in this case, car A actually has a negative velocity. That is to say, relative to the ground, car A is traveling at negative 65 kilometers per hour, and car B is traveling at a positive 45 kilometers per hour. And so the first question is purely about the relative velocity issue. So what we'd like to do is to find out the relative velocity of car A relative to B, and the velocity of car B relative to A. So we want to see if each of these two cars is looking at each other, what would they say is the velocity of the other? Now in this case, this is the deal. The cars are moving at this speed relative to the ground, but the distance between them is closing much more rapidly. So for example, if car B were stationary and car A were simply moving at 65 kilometers per hour, the distance between these two cars would decrease at a rate that would be equal to 65 kilometers per hour. Every hour, the cars would be 65 kilometers closer to each other than they were before, or vice versa. Instead, we cover up the velocity for car A, make car A stationary. In this case, car B is moving towards car A at 45 kilometers per hour, so the distance between them will decrease at that rate, and every hour the cars will get 45 kilometers closer to each other, and this distance will close. But if we put them both in motion, then we need to combine the two velocities. And again, there is a formula, there's a formal way of doing this, but I think that you can just reason out, do you add their velocities, do you subtract their velocities? And what you're really trying to think about is, how fast is the distance between these objects closing? And so in this case, the velocity of A relative to B. So in other words, how fast is car A moving relative to B? So this is the velocity of A relative to B. I'm going to combine the two velocities because clearly as they move towards each other, the distance is going to close much more rapidly than it would otherwise. Now the only question is it a positive or negative view? So if I'm looking from the viewpoint of B, I'm in car B, and I look at A, I see A traveling in the southward direction at the combined So I would see the car moving at a negative 110 kilometers per hour. Now hopefully that makes sense. From B's perspective, A is moving in the negative direction at the combination of the two speeds. It would be the same thing as if car B were stationary and car A were traveling at 110 kilometers per hour. The distance between them would close at 110 kilometers per hour. Or in other words, car A would be 110 kilometers closer every hour of travel. Now, for question B, that's the velocity of B relative to A. It's a similar situation, except the difference is that from car A's perspective, car B is moving in the positive direction. Now you know that car B has a positive 45 kilometers per hour. And I think probably the way to think about this is if you could imagine that we wanted to create this same situation, but I wanted car A to be stationary, then essentially what would happen is the ground would have to move in the positive direction at 65 kilometers per hour in order for car A to be moving relative to the ground at negative 65 kilometers per hour. You can imagine car A being sort of suspended and the whole ground moving forward at 65 kilometers per hour. That would create a situation where car A would move to the south at that velocity. But if you think about the ground moving forward at 65, that's a motion in the positive direction. And so we would end up with the exact same number, as I said, any two objects observing each other and recording the other's velocity will find the same magnitude, 110, but in the opposite direction. It doesn't matter if the two cars are going with each other, against each other, both going in the same direction to the north or both going to the south. It doesn't make any difference. Any two observers looking at each other will give the opposite value but the same magnitude. Now in terms of how long will it take for the cars to pass each other, this is really kind of a standard problem. I know that they have a distance of 125 kilometers to cover. They have a combined velocity of 110 kilometers per hour, and we're looking for the time. And so in this case, we would use the formula that v is equal to d over t, or that v is equal to delta x over t. So we would start with this equation, v equals d over t, or delta x over t. And for this particular example, we would find that if we solve that equation, we would get t is equal to delta x over v, or d. So that's 125 kilometers over 110 kilometers per hour. Or 1.14 hours. So in 1.14 hours, they will pass each other. And an obvious sort of follow-up question is, where will they be located when they make this pass? So how far will each car travel before passing each other? Well, in that case, they both are going to travel at their own velocities, but for this amount of time. So for car A, we're going to have car A traveling with a velocity of negative 65 kilometers per hour for a time of 1.14 hours, sorry. And I would like to know the distance that they are going to travel. And then for car B, that velocity will be positive 45 kilometers per hour for a time of 1.14 hours, and I'd like to know the distance. So for car A, we would use the same formula, and that is that d is equal to v times t. So d is equal to negative 65 times 1.14. So 1.14 times 65, negative 65, gives me a distance of negative 74.1 kilometers. And over on the other side, for car B, we would use the exact same equation. D is equal to V times T. So D is equal to positive 45 times 1.14. And that's 51.3. And obviously, one of the things that we would like to do is to add the two together to make sure that when we add the two together, we get back the original distance, which is the 125 kilometers. So 51 and 74.1, 51.3 plus 74.1 gives me the 125 back. And then obviously we're taking into account slight rounding errors from rounding our time. We actually overestimated the time just slightly. It was 1.136, I believe. So this is the distance that car B is going to travel. Let me say DB, and this is DA, the distance that car A will travel before they pass each other. And then I could determine that the passing point is somewhere here, about 74 kilometers away from where car A started, and about 51 kilometers away from where car B started. And so using this technique of just reasoning out whether the cars are going with each other or against each other, do I add or subtract the velocities, and then keeping very careful track of whether the car is traveling to the positive direction or the negative direction, from this perspective, from each of the perspectives, will the other one seem to be moving in the positive direction or moving in the negative direction? I think you could reason out any problem, any simple problem with relative velocity.